Look at problem 2563. Count the number of fair pairs. This is a daily challenge problem. So here in this video, we are going to explain a solution based on thought and binary search. So in the next video, we are going to explain a solution based on two-pointer sliding window method. So here the problem statement is very short. So basically we are given a zero-indexed integer array called nums. And also we are given two integers, lower and upper. So we want to return the number of fair pairs. So the definition is like this. A pair is, ij is fair if, so they have an order relation, right? And the sum of the two is bounded below by lower and bounded above by upper, right? So in this two examples, the first output is 6, the second is 1. So we are going to walk through example 1. So here the constraints are the following. So first, the length can be as long as 10 to the power 15, 10 to the power 5, right? So in other words, we need to take time complexity into consideration. So the numbers can be positive, can be negative, or 0, right? So same for the lower and upper bound. So with that said, I guess we are ready to look at the main idea. So first, so we don't need to specifically consider the indices. In other words, this requirement in the fair pair. The reason is that as long as two elements in A is such that their sum is in between the lower and upper bound, then they form a valid pair. The reason is that their indices must be different, right? So this is the one point. So as long as you realize this point, then you should be able to think of thought and find the count of valid pair ending at each elements, right? So this is the first part. So the second part is that for a letter, so we are going to regard it as current when we do the coding in the loop, right? In the letter element B, this is the given, for example, then the former elements A can form valid pair AB if this is the case, right? A plus B is in between the two bounds. So then, because B is the thing we are going to consider, so we minus B in both the three expressions. So we get A should be in this range, right? So let's call it star, just for convenience. So therefore, we just need to find all A's before B such that star holds, right? So this can be easily achieved by binary search, right? Because in the first step, we have already sorted the A, right? So here, let me give you a walkthrough for example 1 and see why it's 6, right? Because for these examples, typically you can just walk through naturally, but now let's put it in the algorithm format. So first we sort this array to get this, right? And then the lower is 3 and the upper is 6. So because we consider pairs, we should start from index 1. In other words, we should consider B equals 1 first. Now we need to find the previous A's such that, so the lower minus this number and the upper minus this number. This is the bound of A, right? So A should be in between 2 and 5, but there's no element in between 2 and 5. So this contribution is 0. So now let's look at the first 4, right? So then you use 3 minus 4 and 6 minus 4. Then the number should be in between -1 and 2, but 0 and 1 are both in this range. So the contribution is 2, right? In other words, the corresponding indices for 0 and 1 can form valid pair with the indices for corresponding to the first 4. This is the same for the second 4, right? So because the bound still be -1 and 2, so the contribution will be 2. So for B equals 5, so you use 3 minus 5 and 6 minus 5, you're going to get -2 and 1. So the contribution is again 2 because there's 0 and 1. So now let's look at 7. So in order to get the valid pairs for 7, we need to use 3 minus 7 and 6 minus 7. So the number A should be in between -4 and -1. but in before we don't have -1 and or -4 or anything in between this range, so the contribution is 0. So overall result will be the accumulation of the contributions. That will be 6, right? So another comment is that so let me delete all those and then walk you through line by line. So another comment is that we can consider set decomposition. For example, if we want to find A's such that this is the range, so A should be in this one, right? So then it will be equal to the set corresponding to A less than or equal to the upper bound, and then minus the set corresponding to A strictly less than the lower bound minus B, right? So with that said, let's look at the coding. So the coding now should be a very straightforward, but we let's walk it line by line, right? So we can choose to expose in the full format, but that's not our purpose. I changed the function signature, especially the nums, to be A, just for convenience of writing. So first we are going to sort this. So this is step 1, right? So now we can initialize a result variable. So this will be 0. And then we are going to iterate. As we mentioned, we just need to start from index 1 on the onwards and consider the corresponding elements B's. So for I in range 1 to less n, right? And then we know the low should be the lower minus A and I. So here, let me introduce some more variables so that it can be easier to reasoning, right? So we have a high is upper minus this AI. So what we want to do next is find previous elements A such that A is in between low and high, right? So or I can write it let's do like this. So now first we used the set decomposition to find this. So the so here should be let's say lower minus B. Yeah. So first we want to find all elements to the left, that is less than this number, less than low strictly. So here we are going to use the bisect module. So let's say IDX1. So bisect. So we use bisect left method. So we want to consider only the left side. So the array we are going to search is this, and the element we are going to search is low, and the range we are going to consider is from the beginning end at before I, right? This is the before. So in other words, if we write like this, the search range or the search index range will be 0 to I minus 1, right? So in other words, greater than or equal to 0, less than I. So this ID will be the number of elements that is strictly less than this one. So now consider the next one. So bisect right. So A, we are going to search high, and the search range still be here, but because here we are using right, so in other words, to the left of IDX2, all the element is less than or equal to this high, right? In other words, this number, this set we are computing, right? So then we do difference. So the increment will be the difference. So we don't need to introduce those those variables, but just to demonstrate you the process. So the result will be the accumulation, right? So then we just return the result. So this is the one way of doing the coding. Now let's run it. It passes the 2 test cases. Now let's look at the generic case. Yeah, it passes all the cases. So here, let me first make some prints, right? So here, let's see, print. So current element. So we are considering AI, right? And the next one is IDX2. Let me write first. Then IDX1. And then the increment. So now if you run it, so let's compare with this analysis here, right? So when the element is 1, so the contribution is 0. When the element is 4, so 2 minus 0, the contribution is 2. Similarly, second 4 is 2. And when element equals 5, so the contribution is again 2. And when element equals 7, the contribution is 0. So overall, you have 6. So this is the first example. So the second example, this after you sort, that will be 1, 2, 5, 7, 9, right? So it's only this one. It contributes one number. Because let's see, you will have so 1, 2, 5, and 1, 2, 5, 7, 9, right? So the lower bound and upper bound are both 11, right? So for each number, for example, for 2, you are going to look at 11 minus 2, 9, but no in before. For 5, you are going to look at 11 minus 5, so that is 8. So no element is 8. So for 7, you are going to look at 4, but no 4. For 9, you are going to look at 11 minus 9, that is 2. So that's 1, 2, right? That's why the result is 1. So with that said, I guess that's the first comment. So another comment is a time complexity analysis. So here first, you sort this a sort. So this gives you n logarithm n. So here n, let's assume it's the length of this a. So now if we do the search right here, like this one, the search is logarithm a logarithm time complexity. Therefore, so for each of these, actually it's going to be logarithm. Let's write I, right? Logarithm I. So this just ones, right? So and then so the overall time complexity will be n times logarithm n plus the log I, right? So summation with respect to I in between 1 and n minus 1, right? So the first term is just n logarithm n. The second term, I'm going to write like I will write less or similar. So it's like the summation log 1 plus up to log n minus 1. So let me add one more term, just because just asymptotically doing the analysis. We can imagine n is very large. So the latter term will be logarithm 1 times 2 times n, right? So then you write one more step. So n logarithm n. So plus logarithm n factorial, right? So now we can use Stirling's formula. So n factorial is roughly n logarithm n minus n plus 1. So we can just think of n logarithm n term, right? So overall, it will be n times logarithm n plus n times logarithm n, right? So overall will be n logarithm n. But here we drop some constant. So that's the time complexity for the current way of writing the code. So with that said, I guess that's about it for the current video. So next we are going to consider two-pointer sliding window method in the next video. Thank you for watching.